Okay, we're going to continue on here, like 14, I think, still. So last time before the exam, we were talking and we got into buffers. And again, a reminder that really a buffer is a common ion situation. A buffer is, again, a combination, as we talked about, of really one of two combinations. It is either a weak acid and the salt of its conjugate base, or you can have a buffer that is a weak base and the salt of its conjugate acid. Remember that when we do make a buffer, really both of those things are in the solution to begin with. And that's really what gives it sort of the function it needs to basically work. Also, a reminder that a buffer is not necessarily a neutral solution always. You can make a buffer at any pH you would like the other day you made hopefully something in like the 4.7-ish range in terms of the acetic acid buffer. But what it is a solution that once made will be able to resist really large changes in the pH if you add more acid or base to it. Will it move a little bit? It will, but we won't see the pH swings or a really big swing in the pH if you add acid or base to it. And the reason it's able to do that, as we talked about, I think at the end last time, was because it does have an acid part and a base part in the solution to begin with. When you add additional acid to it, it's able to basically react with the acid and ultimately prevent the formation of free H plus in the solution. Without the buffer sort of there, if you just put that acid in water, which is not a buffer, it would just generate a lot of H plus really quickly, and we would see a fairly big jump in the pH because of that. But basically, the buffer is able to react with it, prevent the formation of free H plus, and keep that H plus concentration relatively constant, and thus also keep the pH relatively constant as well. And same thing, if we added a base to the buffer, it's able really to prevent the formation of free OH minus in solution. Again, if we added a base to just water, which is not a buffer, we would produce a lot of free OH minus in solution. That's important because OH minus and H plus, they are tied to one another. So as one goes up, the other goes down. So by not preventing or producing a lot of free OH minus in the buffer solution, by turn that basically keeps the H plus concentration relatively constant and also keeps the pH relatively constant as well. So that is really the functionality of a buffer. Because it has both of those components, the acid part and the base part in there, it's able basically to handle any additional acid or base that you would add to that solution and to hopefully maintain the pH. It's really able to do that because of the weakness here of the acid or base in the buffer. It is because it is a weak acid or weak base, it's a weak electrolyte, which means it will be able to set up basically a reversible reaction. And what that's able to do is basically keep both of those parts in the solution together. You're able to keep the acid part and the base part in that solution because they are tied to each other in that reversible reaction. And usually if you're making a buffer, kind of like what you did the other day, you add a little bit extra, say, of the conjugate base. So you'll have a good amount of both of those things in solution to begin with. That's why we can never, ever have a buffer that is actually composed of a strong acid or a strong base, because those things will 100% break apart and you will not be able to keep both of those parts in the solution, the acid part and the base part. You'll end up with like just the base part, or you'll end up with just the sort of acid part, but you won't be able to keep kind of both of those things in solution. There is an equation that goes with this and really goes with common ion, and that is the Henderson-Hasselbalch equation, which is the pH is equal to the pKa plus the log of the base over the acid, where the pKa is equal to minus the log of the Ka. As we talked about, I think last time, this is really, the equation you should use always in a buffer situation. If you don't want to use the equation, you don't necessarily have to. You can still do an ice table. The key part, though, if you do an ice table, you do have to have an initial concentration on both sides of the arrow for the weak acid and the conjugate base, or the weak base and the conjugate acid. You need to have an initial of both of those. And that's a very common mistake that people make when they go to do an ice table, rather than use the Henderson-Hasselbalch equation, is they zero out the right-hand side on the initial. And what you just did there is no longer a buffer. It'll be like a weak acid, or if you're doing like a base one, it'll be like a weak base type problem. So you could still use an ice table. The ice table will be made up of the weak acid or the weak base, sort of ice table, Ka or Kb type problem, but initial concentration does need to be on both sides. I did put up there, I think, the other two sort of equations that go with it that you sometimes see, which I'm not such a big fan of, but you can calculate the POH, which is the pKb plus the log of the acid over base. So these guys are reversed in this one when we use the pKb. Again, you do not get the pH here, you get the POH in this case, where the pKb is equal to minus the log of the Kb. And a nice relationship that is maybe helpful in sometimes is the pKa plus the pKb does equal 14. So, sometimes that's a useful sort of relationship to help you get to a pKa value if all you can find maybe is a pKb value. As I mentioned before, you can use the Henderson-Hasselbalch equation, which is in the box for acidic, basic, whatever type buffer you want. Sometimes people in books and stuff, you will see them kind of use this one in a basic sort of situation. It's really not necessary, in my opinion, because in most cases you are interested in the pH, and so might as well just go into the top equation there and get the pH directly. But you'll sometimes see that bottom one. Any questions on any of those things there? Okay, so I think we left off with doing some calculations here, or starting to talk about the calculation. So why don't we start with just A for now, and then we'll talk about B together here in just a second. So for now, just calculate A, which is what is the pH of this buffer system that is 1 molar acetic acid with 1 molar sodium acetate. Here's the Ka value on the bottom there for acetic acid. Okay, let's take a look at this. So they were nice enough to tell us it's a buffer. They're not always nice enough to tell you it's a buffer. So you would be able to hopefully recognize that this is a buffer by recognizing that that is acetic acid, which is a weak acid, and that sodium acetate here would be a sort of conjugate base. So it's key to be able to sort of recognize those things so you understand what type of problem you're dealing with. Again, the same sort of information can be helpful to you. Clearly, you see a Ka value on the bottom that tells you it obviously is a weak acid in that case. And obviously, the acetate and acetic acid are related to each other. So, that should help you focus that. Once you determine that, you really can go right into the Henderson-Hasselbalch equation to calculate the pH here. And so let's do that. So for A here, it would be the pH is equal to the pKa plus the log of the base over the acid. Here, the pKa would be minus the log of the Ka value, which is minus the log of 1.8 times 10 to the minus 5, which is a pKa value of 4.74, I hope. At this point, or you could go right in, which would be the pH is equal to 4.74 plus the log. In this case, the sodium acetate obviously is our base. The acetic acid obviously is our acid. And they are both 1 molar in this case. That basically gives me the log of 1, which is equal to 0. And that gives me that basically the pH here to open up is 4.74. Any questions on that? Now, if you chose not to use the Henderson-Hasselbalch equation and you wanted to on ice table, it is perfectly fine if you're fond of ice tables and love them. What you would want to do is just set up a weak acid sort of ice table where you would have acetic acid dissociating into H plus and some acetate. The key on this table, again, is the initial part of it, which would be 1 molar, 0. And the thing that most people will forget when they come and do this table is the actual value that should go there. That 1 molar would come from the sodium acetate. So the rest of the table would be just like normal, some minus x's, some plus x's. And we would end up with 1 minus x, x, 1 plus x. This obviously, I won't finish it out, but goes into our Ka expression where we would solve for X. X would obviously equal the H plus concentration, and then you could go into the pH, which should circle you back to basically the number that we got up there on top. So again, there's really no preference. It's your preference, whichever way you want to do it in this sort of buffer situation. Henderson-Hasselbalch probably quicker and less room for error probably, but if you're comfortable doing ice tables, you definitely can still do an ice table for this buffer. Any questions on any part of the calculation there? Okay, so then let us look at part B and sort of see what is going on here in part B. So let's go back perhaps. So in part B, what we're going to do is basically take the buffer solution from part A, and then we're going to add some HCl to it. So kind of similar to what you did in lab the other day. You made your buffer, right, and you pipetted in some HCl and some sodium hydroxide into the other buffer. So in this particular example, which is not always the case, but in this particular example, we're going to assume that everything basically is just 1 liter, just to make the math a little bit easier. In normal situations, you won't assume that, so you'll have to use the actual volumes that are there. Now, let's talk a little bit about what happens when we take a buffer, such as this, and I dump some HCl in there. When I add volume, does the molarity stay the same? I see some shaking of heads no, I'm hoping. So the answer is no, it does not, because molarity is moles of solute per liter of solution. So when you mix things together, you add some solution to some other solution, basically this number continues to change, the bottom part of molarity. The part that remains the same is actually the top part stays the same, which is the moles of the solute. Pretty much whatever acetic acid you have in there, or say sodium acetate you dumped in there, is going to be what is in that solution. So one really important lesson here is whenever we take a solution and we add more volume to it, which is very common in a buffer, like what you did in lab, you had a buffer, you pipetted in some acid, you pipetted in some sodium hydroxide, the molarity will change, but the moles will not. Also, in a second, when we start talking about titrations, you're just constantly adding volume, right? Which means the molarity is constantly changing as you're doing a titration. What that means is when we do an ice table in that situation, we should do the ice table in moles. And once you're done with the first ice table, you should then convert it back to molarity using the total volume that is there at that point. So when we look at part B, we're going to add 0.1 molar HCl to this buffer. So 0.1 molar HCl added to our 1 molar acetic acid and 1 molar sodium acetate buffer. So again here, we're going to assume that everybody basically is 1 liter. So we could convert everybody into moles really simply, right? Because 1 liter times the molarity will give us that many moles. When I do add my HCl to this buffer, what is it going to react with? Is it the acetic acid or the sodium acetate? It is going to be the sodium acetate. Again, this is our buffer where this is really the acid part, right? And that's the base part, which means when I add an acid, it should react with the opposite. It should react with the base part of the buffer. And we're really just going to get a double displacement sort of deal here happening. Again, the positive negative and positive negative here are going to switch partners. That will get us acetic acid and a little bit of sodium chloride action happening there on the double displacement there. So we want to do an ice table because there definitely is going to be a reaction that's going to occur. We want to do this ice table in moles. Again, we are adding volume, so we want to make sure that we do this guy in moles. That will stay the constant. So again, since everybody here is 1 liter, 1 liter times 0.1 molar gives us 0.1 moles of HCl. For the sodium acetate, 1 liter times 1 gives us 1 mole of the sodium acetate. Also screwing up in these tables right here, people will zero out this, but I do have some acetic acid here, right? As it is part of the buffer. So we should have 1 liter times 1 molar, which would give us 1 mole in this case, and this guy here would be 0. Any questions on that? Now, if I made my buffer pretty good, what should happen to that HCl that I just added? Should it stay? Should it go away? Should nothing happen to it? All the HCl should ideally go away, right? If we made this buffer right. So different than a normalized table here, when we're doing it in moles, we actually do know what the change should be. The change should be when you add that HCl to that buffer, it should all get used up. So we're actually going to use a number here, and that number is going to be the HCl moles. It's going to be minus 0.1 moles, minus 0.1 moles, and plus 0.1 moles. Now, how do I know that that's going to get used up? Well, if we just simply look at the numbers here, that is 0.1 and that is 1. Which one is like the limiting reagent here? It's just smaller number. So at this point, the HCl is like the limiting reagent, right? We got tons of sodium acetate to react with it, not a problem. That's going to take us to equilibrium here, which will give us 0 of that guy. I am going to grab my thing here because it's been a long day. So we'll do that. There we go. So that's going to be 1 minus 0.1. That's going to be 0.9 moles at this point. That is going to be a 1.1 without the use of a calculator there, which will be the moles of that. By the way, I really didn't fill much in here on sodium chloride. Any reason why? What is sodium chloride? It is a salt, and is what type of salt? It's a neutral salt, which means it's not going to screw up the pH. Probably best not to throw numbers down that you might want to try to use wrongly somewhere down the road here. So I'm just going to ignore the sodium chloride. You can put the numbers, but really you're just going to ignore it at the end anyways. So best maybe not to lay up some numbers. At this point, trust me when I tell you, even though you don't technically have to do it at this point, but you should do it, and it will serve you well in later calculations that we do. After this first table, you want to then convert everybody back to molarity. It's a very good idea to do that. We would be dividing at this point by the total volume. In this case, obviously, we're keeping it at 1 liter. But again, you know, for example, you had, say, 25 milliliters of your buffer the other day, right? And you added like 1 milliliter, right, of the HCl. That gives you a grand total of 26 milliliters, right? And that's what you would be dividing if we were doing like the other day, converted to liters, obviously. That's going to give us 0.9 molar. We'll divide this guy by 1 liter, gives us 1.1 molar. Now, at this point, you did this ice table, you're happy with yourself, you're proud of yourself for doing that, and you should be, but maybe you're not sure what's going on at this point. So again, the ice table does give you a lot of information. If we look at the ice table, we can see what we have left over at this point, which is basically sodium acetate, and we have some acetic acid. Again, you should still recognize that as being a buffer still, this left over at this point. So we still have a buffer, and that's going to help you with basically getting us to the pH. You have 2 options. Again, you could do an ice table if you wanted to, or you could just go right into the Henderson-Hasselbalch equation. That is what I'm going to do. I'm going to go with the pH is equal to pKa plus the log of the base over the acid. It is still acetic acid, right, that we're dealing with, which means the pKa value is the same as what we had before, which is that 4.74 number, plus the log of the base, which is still, again, our sodium acetate, which means our 0.9 should go up on top, and our acid on the bottom, which is 1.1. All right. So that is going to give us 0.9 divided by 1.1. We're going to take a little log action of that. Going to add that to a 474. We're going to end up with a grand total of 4.65 as our pH here. Again, you can do an ice table. Your equilibrium of the first table would become your initial of the second table. Go into your Ka, solve for X, and obviously you'll get the same answer. Question on any of those steps there? Now, does this make sense based on what we just saw in part A? Well, in part A, we had just the buffer by itself, which was 4.74. We added acid to it, and it went down to 4.65. Not a tremendous jump in pH, right? Which means our buffer is kind of working. The other way that I should be looking at this is, did it actually move in the correct direction? It did, because I added acid, so it should have went down a little bit, right? So, you know, it should go down a little bit. A buffer should be able to maintain giant jumps in pH. Any question on how to do this type of adding to a buffer? So the other day we talked about, you know, there is a limit to buffer capacity, right? So we can use like this guy here, I think. So if we use the same buffer, right, and we had 1 molar of our acetic acid, and we had 1 molar of our sodium acetate, and you know, we'll keep everybody still at 1 liter just to keep the math pretty simple. Maybe you didn't read the instructions, and maybe you didn't grab the 0.1 molar HCl, but you know, you thought the 18 molar HCl looked pretty good. So you decided to grab the 18 molar off the shelf instead of the 0.1 molar. So if we were to do this, we would have our same reaction, right? Our HCl plus our sodium acetate going to give us our acetic acid and our sodium chloride. Again, we'll keep everybody at 1 liter, which means initially here I would have 18 moles, right, of my HCl. I would still have my 1 mole of my sodium acetate and my 1 mole of my acetic acid. Now when I dump that in, and before you come up to me and ask, is it a big deal that I grabbed the wrong one and added it, right? What's going to happen here when I add the HCl? Which one now becomes like the limiting reagent? It's going to be the sodium acetate, right? Smaller number, which means what's going to happen is it's going to try its best, right? But it's only going to be able to take care of like 1 mole of that guy, right? And it's actually going to be what is used up there. And what we will end up with now at equilibrium is we got like 17 moles of this guy, we got none of this guy, and now we got a couple of moles of this guy, which we obviously can convert back to molarity at this point. What we're left with at this point is acetic acid, which is a weak acid, right? And we're left now with hydrochloric acid, which is a strong acid, right? So basically, this is just going to dump a ton of H pluses in there, right? We no longer have a buffer. We basically just blew through our buffer in this situation. And we definitely would see a ginormous jump in the pH at this point, because basically your buffer can handle it. It can only handle about that much. So when we talk about sort of a buffer and things reacting, it really is the moles of what's in there that's available to react. And there's only so much that's available to react. And that's why when you make a buffer, it's important to make it with the right concentration and to think about what you're going to be adding to it to make sure it can handle, you know, the change that would occur. Any questions on that there? Yeah. Yeah, it's not okay if your purpose was to make a buffer correctly, you know, for the correct situation or whatever you're doing. Ideally, the buffer really should maintain its pH. It should go up or down a little bit, You know, depending on the situation, if you're just like had a random buffer and you want to know would it work in that situation, you know, it may work or may not work, and you could do the calculation and you might see a pretty big jump. So if you ever did a calculation, you saw a really big jump, technically speaking, it could still be a buffer, but it's probably not the best buffer for that situation because the goal is you really want to kind of maintain the pH. Yeah. But ideally, a buffer really shouldn't see a big swing in pH. Should see gradual swings in whichever way you add it. And actually, when you make a buffer, if you really like measured out everything and threw everything together, and you put the pH meter in there, it typically is not usually exactly the pH that you were aiming for in your calculation because you know, sometimes you may make a buffer out of something that's a solid, right? Not necessarily a solution. And if you ever weighed out a solid, right, it's very hard to get exactly to the nose, right? The amount of grams that you need. Some stuff gets lost, some stuff stays on the weigh paper, it doesn't get in there. So what we typically do if you were to make a buffer is you'd make a buffer. It should put you pretty close in the ballpark of what you were aiming for. And actually how you adjust it to the correct pH is you take like a bottle of acid or a bottle of sodium hydroxide or base, and you add some drops. You just kind of drop in there until the pH gets to, you could kind of dial it into exactly the pH that you're looking for. So in real life, I made a lot of buffers, and they never end up exactly like what you're supposed to be at, and you typically do need to do a little bit of adjustment. And because they're a buffer, you're able to do that. You're able to, you know, add acid and base without those big jumps in pH. So you can add and very slowly either raise the pH if you needed to, or lower the pH and really dial it into the pH that you need. Other questions on that? Okay. Buffers. All right. So now let us try another one here. Calculate the pH of ammonia and ammonium chloride buffer. What is the pH after you add 20 milliliters of 0.5 molar sodium hydroxide to 80 milliliters of the buffer? We are not holding the volume constant, so you do need to take the volume into account here to calculate things like moles and things like that. Let me also give you a Ka value. Let me try to remember what my Ka value will be here. Let's go with... sounds good. Let's go with a Ka value for NH4 plus of 5.6 times 10 to the minus 10. All right, take a few minutes. You should end up with two answers. One, what is the pH of the buffer before you add anything to it? And second, what is the pH of the buffer after you add some sodium hydroxide to it? And you're going to be adding to 80 milliliters of your buffer. So you got a beaker of 80 milliliters of buffer. You're then going to add 20 milliliters of base to it. So see what you come up with. Again, two answers for this guy. Again, if they did not tell you it was a buffer, you should hopefully be able to recognize NH3. That is a weak base. And really here it is NH4 plus from the NH4Cl. That is its conjugate acid. That would work better. Conjugate acid in this case. Again, the Cl is really just a spectator ion in this case. It is actually the NH4 plus. This is sort of the buffer part of it. We can find a Ka value on the table, which was given to us. So if you weren't sure, you should know that this guy here obviously is the acid part of the buffer. So even if you didn't know that NH3 was a weak base, you could probably make an educated guess that that is the base part, since the Ka value, right, goes with the acid. That means since this really is a buffer, we could go right into the Henderson-Hasselbalch equation, which would be the pH is equal to pKa plus the log of the base over the acid. Here, we would want to get the pKa value here, which would be minus the log of 5.6 times 10 to the minus 10. That hopefully should give us like a 925, 9.25, I believe. Let's see here. That means that this is going to be 9.25 plus the log, and it's important here to always put the base up on top when you're using the Henderson-Hasselbalch, and that is the NH3, which should be this number, should go up on top. And our acid should go on the bottom there, and that would open us up here with a opening pH of something plus like a 925 or a 9.17 as the opening pH here. Any questions on that? Clearly, we have not added anything to the buffer, right? So we don't have to do anything in moles or worry about it. By the way, you can, in the Henderson-Hasselbalch equation on the base over acid part, you can do it in moles. It comes out the same because the volume on top and the volume on the bottom will divide out, and it will actually work the same. It's best to convert it back to molarity because there will be other instances where you do need molarity and moles will not work. But technically speaking, you could go into the Henderson-Hasselbalch equation with moles of each of these guys, and it will work out okay. But again, make sure you convert it over so you don't run into those other situations where it will not work okay. Now, this is an acidic basic neutral buffer. This is a basic buffer. So just to kind of show you the other way that sometimes people will approach this, let's say you look in your book and go, oh, I can't find this guy on a Ka table, which might be the case, but you would be able to find this guy on a Kb table with its Kb value of 1.8 times 10 to the minus 5. And so how would you want to work it? Well, you could use that other equation. The POH is equal to the PKB plus the log of the acid over the base. You could just convert this guy into your PKB value, which is done the exact same way, minus the log of the KB value. That gets us minus the log 1.8 to the minus 5, gives us a 4.74. And putting that into our equation here would give us 4.74 plus the log. The important part here, though, is in this one, the acid needs to go up on top, which means we should put 0.36 divided by 0.3. And a reminder that this does not give you the pH. This is going to give you the POH in this case. And when you do that, 0.36 divided by 0.3, a little log, and a little 4.74. Going to give us like a 4.82, we'll call it, on the POH, which again, as I said before, then you got to subtract 14 from it and to get yourself to the pH, which in this case would give you like a 9.18. So fairly close to what we got. The difference is in the rounding of the KB value. The real value for KB is like 1.7895. And if you use that, you'll end up with 9.17, but that's the difference there. So again, I personally don't see a benefit of doing the bottom one, so you got to subtract 14 anyways. Might as well just go into the top and calculate it that way. But again, just in case you could not find the Ka value, but just that Kb value, that's the way you could do it. The other way you could do it is you could get your Kb value here and do that the pKa plus the pKb equals 14 and solve for the pKa value from that pKb value. Then you would have a pKa value that you could go into here and use the Henderson-Hasselbalch equation on top. So that's another way you could do it as well. So there's multiple ways you could get there if you maybe can't find the correct value you're looking for. Again, you might want to do the last one there, get the pKa value, and just still go into the Henderson-Hasselbalch so that you could get the correct pH. Yeah. You could do that as well. So that's what you could do as well. Yep, that will get you your Ka, and then you could go that way as well. So again, there's multiple ways you could do it. Again, sometimes you may be given like a pKa value or pKb value rather than a Ka or Kb. So, you know, knowing how to kind of go between them is useful as well. But definitely that will get you there as well. Any questions on the first part? There are 9 different ways to get it done there. All right. All right. So let's talk about the second part. In the second part, we're actually adding, like I said, we have basically 80 mils of our buffer here. So we got a beaker with 80 milliliters of our buffer, and we're going to add 20 milliliters with sodium hydroxide, I believe, into basically our buffer there. And we want to know what the pH is. So that's 0.05 molar sodium hydroxide, 0.05 molar. And our buffer there was 0.3 ammonia and 0.36 molar ammonium. Okay, so we're definitely going to add the sodium hydroxide here. By the way, the 80 milliliters comprised of both parts of the buffer, right? It's all together floating around in the same total volume for the buffer. So basically, we can think of it as having 80 milliliters of ammonia and 80 milliliters of ammonium. When I add sodium hydroxide to that buffer, which one is it going to react with? Sodium hydroxide is a strong base, right? So it should react with the base part or the acid part of the buffer? The acid part. The acid part of the buffer would be which one? It would be this guy, yeah, that is the acid part of the buffer. So those are the two that should react. So that's what we will get here. We will have our sodium hydroxide reacting with our ammonium. You can leave the chloride if you want. Do you want me to leave the chloride or take it off? Nobody knows. Take it off. All right, we'll get rid of it then. Of the ammonia there. When that reacts, obviously in this case, we're going to form a little bit of water, I'm assuming, as this is going to act as an acid and donate it. We will also form some ammonia. And by the way, if you left the chloride, that's what would end up with the sodium there. And by the way, it would end up with the chloride at that point. So I'll just parentheses the chloride up there. So that's where it actually end up. Not that it really matters, the chloride, right, or the sodium, because it's like a neutral salt. So don't even have to really worry about it in that case. At this point, we do want to do this table in molarity or moles in this case. We do want to do it in moles, right, because we are adding volume. So we want to get the moles of everybody here. So we'll do the moles of our sodium hydroxide first. We got to take 0.02 liters, which is converting 20 milliliters into liters. We need to multiply it by the molarity there of our sodium hydroxide, which is moles per liter. The liters cancel, and that gets us a 0.02 times 0.05. And 0.001 mole here of our sodium hydroxide. We want to do the same thing for our buffer. So we're going to basically take 0.08 liters, which is our volume, and we're going to multiply it by both of these guys individually. So we'll take 0.080 times 0.36 for our NH4 plus, which would give us 0.0288 moles. Again, we would take 0.08 for our 80 milliliters and times it by 0.3 molar to get our moles of the ammonia on this side. Any questions on how to do that? Yeah, everybody's good on that? Yeah. Again, water, I'm not going to be too concerned with, so I'm not going to throw any numbers down. Again, this sodium chloride, I'm not going to be really concerned with, so I don't try to use numbers maybe where I shouldn't use them. At this point, if this is a good buffer, the change should be which one? should be the sodium hydroxide, right? Cannot have a negative number, so always got to be the smaller number. You're going to run into that later, and you're going to want to do it, and you end up with a negative number. Don't do it. Yes, so that's a good way not to screw up. Don't make a negative number at the end. So this is going to be minus 0.001. That's going to be minus 0.001, and that's going to be a plus 0.001. I got all the zeros there and didn't lose any along the way, hopefully. That it means that we will hopefully have used up all of our sodium hydroxide, which we hope we did. 0.0288 minus 0.001, going to get us a 0.0278 moles of this guy. We're going to take 0.024, and important here to add, not subtract, 0.001 on the right-hand side there, going to get us 0.025 moles. Any question on the ice table here? At this point, just convert it back to molarity to be safe in all situations going down the road here. To convert it back to molarity, we need the total volume to do that. What is our total volume here? It is 100 milliliters, right? We started with 80 in the buffer. We added 20, which means our total volume would be 100 milliliters total volume. That means that we technically will be dividing each of these by 0.1 liters, right? Which is 100 milliliters converted to liters. And that will get us 0.25 molar and 0.278 molar, I believe, at that point. Any questions up to there? Yeah. You know, you could, if you can go into the Henderson-Ausbach equation, all that will work as long as it's the same. I probably would. You can. It will work if you want to do it that way. It should come out okay. Yeah. As long as at the end you divide by milliliters at the end, it should come out the same. Yeah. Yep. I'm sorry, which number again? I'm sorry. Right here? Right. That one? Yeah, so the molarity of the sodium hydroxide was 0.05 molar, which is 0.05 moles per liter. So that, when we multiply by the volume in liters, will cancel out and give us moles at the end. Yeah. And again, we do want to do this in moles so that, because that again will remain relatively constant, even though we're adding volume, the molarity will not. So you don't want to go into this table with the molarity. Other questions on that? All right, so you did this whole table, and again, maybe you're still not sure what is going on here, you know, in terms of what's happening. So don't overlook your ice table. Again, you literally could just circle what you got left at this point. And again, hopefully you could still recognize these two guys as being related to each other as a weak base and as conjugate acid, which again should tell you you still have a buffer happening at this point. And again, that should point you in the right direction as to probably going into our Henderson-Hasselbalch equation. Again, you could do an ice table if you prefer. The Ka value here, or the pKa value, is going to be the same as what we had previously, which would be 9.25 plus the log of our base, which again in this case is the ammonia here. That is going to be 0.25 divided by 0.278. And gets us a pH at this point of 9.20 in this case. Any questions on that one there? Again, we can take a look. When we started here, we had a pH of 9.17, right? We added base to it. We didn't see a big jump in pH. It went up to 9.20. and it did go in the correct direction, which is up because we added base to it. So again, these are things you want to think about when you get your answers. I can't tell you maybe how many times I've seen people calculate something like this, and they started with 9.17, and maybe they end up with, on this part of the calculation, like a 7 point something. And obviously, just by knowing that when you add sodium hydroxide, it should go up, that should be a very big red flag for you that you definitely went way too far, probably down, and also in the wrong direction, right? Question on buffers and adding acid or base to buffers. So obviously you need to be able to calculate a buffer pH. You need to be able to calculate the pH after you add acid or base to it. The key is when you add, you got to do that first ice table in moles. Also different is you actually have a value for the change part. Should be the limiting guy, the smaller number. And at the end of that first ice table, convert it back to molarity, and you'll be in good shape for any calculations that sort of come after that. Any questions on buffers? Okay. Then we're going to talk about the next big topic, which is titrations. Everybody's favorite. Yes. All right. So titrations is a technique that we typically use when we're trying to find something that's an unknown. So usually when we do a titration, we have a standard solution or some type of solution that is basically a known solution. We know the molarity of it. We know obviously how much volume we're using of it. And we typically will add it to a solution that is unknown. Maybe we don't know the molarity of it. Maybe we don't know other things like molar masses, equivalent weights, those type of things. When we do a titration, especially acid-base titration, we either add acid to the base or base to an acid. We use a burette, right? And so, for example, we can have the base up in the burette. We could have our acid down below, and obviously we continue to add it. We continue to add it in an acid-base titration until we hit what is known as the equivalence point in the titration. The equivalence point in the titration is the point where the reaction is complete. It is the point where in an acid-base titration, the moles of the acid equals the moles of the base. So that is your equivalence point, the point when those two guys exactly equal each other. How do we know when we reach the equivalence point? We typically use some type of indicator. An indicator, as we did in the other experiment as well, works over a pH range, right? And they have different colors depending on sort of the pH. If it's the acidic part of the buffer, the acidic part of the indicator or the base part of the indicator. Most common one used a lot of times is phenolphthalein, yes, and I think we use it better way. Phenolphthalein has a pH range of like 8.3 to like 10-ish. At 8.3, it is actually colorless. And gradually, I know I got green on the screen, but gradually becomes pink as you go this way. St. Patrick's Day, we'll go with green. So you got pink, super dark pink, yes, all that kind of stuff. When you typically do a titration with phenolphthalein, do you want super dark pink or you want the lightest color pink possible? You do want the lightest color pink possible, like you got to put like a white piece of paper under there, hold it up, and like, I think I see it, right? And the reason for that is we do want to pick an indicator that will actually change color near the equivalence point. So that's the purpose of the indicator, is to actually change color near the equivalence point. And probably most titrations that you do or have done, the equivalence point is actually like right around in this ballpark, in that colorless range, actually, which is why they typically will tell you want the faintest color of pink possible, because if you stop at that point, you should be stopping pretty close to the equivalence point. If you go really dark pink, you might find yourself way over here, right? Pretty color, I like it, but you might be like at a pH of 10 and completely miss the equivalence point. Or if you're really careful and you went super dark pink, maybe you didn't really miss the equivalence point all that much. Very common thing that most people have say when they titrate is, I just added 1 drop and it went from like colorless to like super dark pink. Yes, I think I heard some of that last semester as well, right? And we're going to explain why that actually happens, why when you just add 1 drop, do you see such a big color change? And, you know, maybe it's not all that important. You know, if it goes really dark pink, if you're really careful, that is a nice shade of pink, maybe lighter. So we're going to talk about some different types of titrations. So the first type of titration we're going to talk about is a strong acid, strong base titration, like what is on tap here in about 30 minutes. Yes, in the lab. So just so everybody has sort of the right orientation of what is going on, we have in the burette your sodium hydroxide, and we are adding it to the HCl. So this is what we call a titration curve here on the left. We have pH on the Y, and we have volume of base basically on the right-hand side here. And this is your typical S curve that you see in a titration, like you will make in about 40 minutes or so. So there's really in a titration curve kind of 4 parts, and we're going to talk about the different 4 parts here in just a second. But there's kind of like the first part here, which is like before you add anything. So before you really start the titration, before you added any sodium hydroxide. Then there is like a second part of a titration curve that takes you from the very first drop. I think I just did a coffee commercial there, until basically you hit the equivalence point, right? And that is like the second part. The third part of the titration curve is dead on the equivalence point. And that's usually where you stop most of your titrations, but not you, because we want to continue on here and get the entire curve. So the fourth part is pretty much after the equivalence point, and we're continuing to titrate. So we do see this sort of characteristic curve that occurs. So let's talk about what is happening in each of these spots. So let's start with the very first spot there before we add any sodium hydroxide. Right? So before I add any sodium hydroxide in this particular case, what do I have in the beaker? Yeah, I have just HCl, right? So if I wanted the pH at this point, how could I get the pH of HCl? HCl is a strong or weak acid? It is strong, which means it's going to 100% break apart, right, into H plus and Cl minus, which means that will give you the H plus, which means you could go right into the pH equation at the very beginning here of the titration before you add any sodium hydroxide. Because we have not added any sodium hydroxide, we could use the molarity, right? Because it has not changed. It's just sitting there. You haven't added anything to it. So that's not too bad. You just go right into the pH equation and you're good to go, right? Any questions on that there? Okay, so now you decide, well, I think I like to add. So now we're in this region here, the second part of the curve. So now we're starting to add some sodium hydroxide. When I add sodium hydroxide in this case, I am going to get a reaction, right? And it's going to be a reaction between hydrochloric acid and sodium hydroxide, which is a reaction of a strong acid and a strong base, which means you make a salt and water, right? And we will make water. And the salt here will be sodium chloride. All right. So we do need to do an ice table here because we are adding. There's going to be some reaction that's going to occur, and we want to kind of figure out what's going to happen at the end. So because we are adding volume here, should I do this ice table in molarity or moles? We should do this ice table in moles. So we do need to do this in moles. So I'm just going to make up this number. So let me just say that one more time. I'm just making this number up out of thin air. I'm going to say we are starting with 4 moles of HCl. Again, just made it up. Yeah. This is obviously what we're starting with in our beaker, right? And this is what we're adding to it, right? Now, if I am before the equivalence point, should I have less moles, equal moles, or more moles of sodium hydroxide that I'm adding? It is less. And if you're not sure about that, at the equivalence point, the moles of acid equal the moles of base, right? So at the equivalence point, that's what's happening, which means if I have not got there, I have not added enough base to get equal amounts, so I should have less. Again, just making up the number, I'm going to go with 2 moles, which is less. I'm going to have 0 over here. What should happen at this point is the sodium hydroxide is really the limiting reagent, right? I have enough HCl there to kind of react with it. So the change here is actually going to be the amount of sodium hydroxide I'm adding. That means that when I reach equilibrium, I will have 2 moles of this guy, none of that guy, and a couple moles of this guy. Now, like we just talked about before, at the end of this ice table in moles, I probably should convert that number back to molarity. Total volume here would be how much HCl was in my beaker to start with, and how much sodium hydroxide I just dropped into my beaker from the burette, right? Final volume minus initial volume from the burette. That means I'm going to take both of these guys and really convert them back to molarity using the total volume. And at this point, I really can look at my ice table to see what I got going on. I have obviously HCl left over, and I have sodium chloride left over. Let's start with the sodium chloride. Am I concerned about that messing up my pH? I am not in this case. This is still a neutral salt, which means I'm not really concerned about it. That means I have left over really still hydrochloric acid, which is still a strong acid, which means at this point, this guy will equal pretty much the H plus concentration, which means at that point, you then could go into the pH equation and solve for it. So in a titration of a strong acid, strong base, you need to do an ice table. And the purpose of the ice table here is to really figure out how the concentration of the strong acid changed as a result of reacting with the sodium hydroxide that you added. Once you have kind of the new concentration of the strong acid, still a strong acid, you can use that to get the H plus concentration and then use that obviously to get to the pH. Any questions on part 2? That is pretty much what you would do from the very first drop until you reach the equivalence point. That is how it should end up. You should have your HCl left over, concentration will change, and you can figure out your pH. The pH should start to go which way at this point as we're adding sodium hydroxide? Just start to rise, right? We're using up some of the HCl, we're adding some OH to there, less H plus free in the solution at that point. And that is what we see. As we start adding, moving this way, and approaching the equivalence point, we see that as we get to the equivalence point and heading up to the equivalence point, we are going pretty vertical, yes? And because I'm going pretty vertical, this is why you hear people say, I just added 1 drop and it went super dark pink. When I go vertical, am I adding a lot of volume? I am not. But what is happening to the pH as I go vertical? There's a very big jump in pH. So even like 1 drop too much or 2 drops too much will take your indicator from like a pH of 8.3 to like a pH in 10-ish region. And your indicator will go from like no color to super dark pink. And you just added like 1 or 2 drops, maybe too much. Is that really critical in this point? If the equivalence point's right here and you ended up right here? The answer is no, it's not really that bad in terms of calculation, because if you go straight down, they're about the same volume, right? And that's kind of what you need to get to the equivalence point. What is bad is if you're not really careful and you're not really just like missed it by a drop in, like titrated like me and opened it up, just let it flow down and then shut it. You would have the same pink color way over here, perhaps, yes? Which means you really missed the equivalence point. So if you're really careful as you're titrating in like a situation like in 200A, and you were careful and you just added one drop and it went from like colorless to like super pink, hopefully your instructor didn't make you retitrate it, because it really didn't matter in the end, because you weren't that far off if you were really careful. But the reason they will tell you want super light pink, and maybe they'll tell you to redo it, is because they don't know if you just opened it up and you really did shoot way past it. So, if you're really careful in titrating and you miss the color, it's really not that important. And that's why I used to tell my class that it's more important that your volumes are relatively about the same, because then you hopefully should be near the equivalence point. Any questions on that and why it turns pink? All right, so let's talk about what happens at the equivalence point in this type of titration. That would be right here at number 3. So at the third point here, which is the equivalence point, we're going to still have our reaction of HCl plus our sodium hydroxide. We're still going to need to perhaps do an ice table here. So if we did an ice table, again, just making up the number of 4 moles of what we're starting with. And this is what we're adding, which is our sodium hydroxide. How many moles of sodium hydroxide should I have at the equivalence point in this case? We should have the exact same amount. So that's a good thing to also keep in mind, because you might have to work backwards to figure out volumes and stuff like that. So if you know the moles that you should have, and you know the molarity of the sodium hydroxide, you can figure out the volume that's needed to get there. By the way, if it's a 1-to-1 relationship, you could do M1V1 equals M2V2 and figure out the volume needed to reach the equivalence point. Sometimes in problems, they don't tell you the volume to reach the equivalence point. You have to kind of figure it out. At this point, it will be 0. Can't screw this up because they're all the same number, so it's got to be 4 as the change here. That means nothing here, nada there, which is what the equivalence point means. We got 4 moles of our sodium chloride, which we could use the total volume to convert back to molarity. At this point, the only thing really in that solution is the sodium chloride, which you're now going to tell me is, again, what type of salt? It is a neutral salt, which means the pH at this point should be 7. No real calculation actually needed in this type of titration at the equivalence point. You will always end up, when you have a strong acid, strong base that comes together, with a neutral salt that should not go through hydrolysis and should give you a pH of 7, as we see here. Lucky number 7 right there at the equivalence point. Yes. Any questions on that? All right, so it turns pink. That doesn't destroy you out. You're like, I'm going to keep going. I'm going to keep adding because I like the pink color. So you go past the equivalence point here in the number 4 region. So let's talk about what happens when we go past the equivalence point. Still going to have the same reaction here of HCl plus some sodium hydroxide, giving us our same reaction of a little bit of water, a little sodium chloride action. So initially, I am going to go with my 4 moles one more time, made up there of what I am starting with my HCl. Again, I am adding my sodium hydroxide. Now that I am past the equivalence point, should I have less, equal, or more moles of the sodium hydroxide? We should have more, right? Because at the equivalence point, they're equal, and that didn't stop you, so you're just going to keep adding, so you should have more. Again, just randomly making up this number of 6. Seems like a nice number. So what happens at this point is, which one is actually the limiting reagent in this case? Yeah, we actually get a flip. This guy now becomes the limiting reagent. This guy you have plenty of because you just kept going, which means the change here is actually going to be The HCl in this case is going to be the 4, the -4, and the +4, which means when we are done here, 0, we got a couple moles of that guy. We got some 4 moles of this guy. And by now, we will be converting this back to molarity using, again, the total volume that's been added, plus what you started with, right? That was in the beaker to begin with. At this point, if we look, we got some sodium chloride, we got some sodium hydroxide, this a buffer. I'm going to say no. Want to agree with me? I agree with you as well. Yes, this is not a buffer. This is a situation where we talked about earlier. I have the Henderson-Hasselbalch equation. I got 2 numbers. I feel like, hey, I should probably use that, and this would be incredibly wrong here. What we do have going on here is, by the way, none of these two are related to each other other than they both have sodium. This, again, is still our neutral salt, right, which we're not going to worry about because it's neutral. So really what we're left with at this point that is important in terms of the pH is the other guy. Again, why you should look at your ice table, it gives you important information. This is a strong base, right? Which means because that's a strong base, it will 100% break apart, which essentially means that this guy right here is your hydroxide concentration. That will not let you get the pH directly. It will let you get the POH, right? Which then you could subtract 14 and get yourself to the pH. And this makes sense because you went past the equivalence point. Pretty much at this point, you're just dropping hydroxide in there, right? And you're just adding OH minus, which means we should expect the pH at this point to be pretty basic. And that is why when we look at the curve, once we pass that equivalence point, we just dumped a lot of hydroxide really quick. We get a pretty big jump in pH. And then at some point, it will start to level out at the top part of it. And that's typically what you see in a titration curve. As you approach the equivalence point, you kind of see a big jump to the equivalence point. And then you typically will see a second jump after the equivalence point, and then it will kind of level out at the top of it. Those are the 4 distinct parts in this specific type of titration. And only for this type of titration, strong acid, strong base. There are other types which we'll talk about next time, but I guess we covered what we're doing today in lab, which is this. You're going to do this in lab, make a beautiful titration curve. Hopefully there's not so much scribble on it. Any questions on any of that stuff here?